In this module, you will learn about geometric progressions. Observe the pattern in the sequences shown. Following the same pattern, let's try to write the subsequent terms in each case. Beginning with the first sequence. The first term of this sequence is 10. The second term is 20. The third is 40. The fourth, 80. The fifth, 160. And so on. The ratio of the second term and the first term is 2. Also, the ratio of the third term and the second term is 2. Likewise, if we find the ratio of each term to the term just preceding it, we find that it is 2. Hence, we can generalize that the ratio of the n plus 1th term to the nth term is equal to 2 for all n greater than or equal to 1. It implies that n plus 1th term can be obtained by multiplying the nth term with the constant 2. Therefore, the 6th term is 2 into the 5th term, which is equal to 320. The 7th term is 640. We can find the other terms in a similar fashion. Similarly, for the second sequence, the ratio of n plus 1th term to the nth term is equal to 1 by 2 for all n greater than or equal to 1. It implies that the n plus 1th term can be obtained by multiplying the nth term with the constant 1 by 2. Hence, the 6th term of this sequence is half of the 5th term, which is equal to 1 upon 64. The 7th term is half of the 6th term, which is equal to 1 upon 128. The subsequent terms can be found in a similar manner. Such sequences, where each term, except the first one, can be obtained by multiplying its preceding term by a non-zero constant, are called geometric progressions. Mathematically, a sequence is said to be a geometric progression if each term, except the first one, can be obtained by multiplying its preceding term by a non-zero constant. This constant is called the common ratio and is obtained by dividing any term, except the first term, by its preceding term. It is denoted by R. Let us now consider a GP with the first term, A, and the common ratio, R. Then the second term of this GP is obtained by multiplying the common ratio, R, with the first term, A. The third term is obtained by multiplying the common ratio, R, with the second term. The fourth term is obtained by multiplying the common ratio with the third term, and so on. In this way, the subsequent terms can be obtained. Likewise, the nth term can be obtained by multiplying the common ratio R with the n minus 1th term. The nth term is also known as the general term of the GP and is denoted by A with subscript n. With the help of the general term or the nth term, we can find any required term in the sequence without actually finding the preceding terms. Thus, we have the general form of GP as shown. Now notice that the terms of a GP follow some definite pattern as shown. The first term, A, can be written as A into R raised to the power of 1 minus 1. The second term, a into r, can be written as a into r raised to the power of 2 minus 1. The third term, a into r square, can be written as a into r raised to the power of 3 minus 1. The fourth term, a into r cube, can be written as a into r raised to the power of 4 minus 1. This pattern suggests that the nth term of the GP should be given by a into r raised to the power of n minus 1. Remember that the nth term is also called the general term of the GP. Here the common ratio, r, is defined as the ratio of any term except the first to its preceding term, and is expressed as n plus 1th term divided by the nth term for all n greater than or equal to 1. A finite GP has a finite number of terms, while an infinite GP has an infinite number of terms. Correspondingly, the sum of the finite number of the terms of a geometric progression is called a finite GP series, while the sum of the infinite number of terms of a geometric progression is called an infinite GP series. Consider a GP with n terms, having the first term as a and the common ratio r. The sum of these n terms of a finite GP is a finite GP series. Let's denote this GP series by Sn. While finding the value of Sn, two cases arise. The first case is when r is equal to 1. Consider a GP with n terms, having the first term as a and the common ratio r. The sum of these n terms of a finite GP is a finite GP series. Let's denote this GP series by Sn. While finding the value of Sn, two cases arise. The first case is when r is equal to 1. The sum of n terms of the series is equal to a, so on, up to n terms. This is equal to n into a. The second case is where r is not equal to 1. Multiplying both the sides of equation 1 by r, we get r into Sn is equal to a into r plus a into r square plus a into r cube plus so on, up to a into r raised to the power of n minus 1 plus a into r raised to the power of n. Denote this by equation 2. Now, subtracting equation 2 from equation 1, we get Sn minus r into Sn is equal to a minus a into r raised to the power of n. This further implies 1 minus r into Sn is equal to a into 1 minus r raised to the power of n, or Sn is equal to a into 1 minus r raised to the power of n divided by 1 minus r if r is less than 1, and a into r raised to the power of n minus 1 divided by r minus 1 if r is greater than 1. The general term Tn of a GP is equal to the sum of the first n terms minus the sum of the first n minus 1 terms of that GP. Let's now have a look at some simple tricks to find the terms of a GP when their sum is given. When we have to find an odd number of terms in a GP whose sum is given, then it is convenient to take the middle term as a and the common ratio as r. Thus, three terms are taken as a upon r, a, and a into r, while 5 terms are taken as a upon r square, a upon r, a into r, and a into r square. When we have to find an even number of terms in a GP whose sum is given, we take a upon r and a into r as the two middle terms and r square as the common ratio. Thus, 4 terms are taken as a upon r cube, a upon r, a into r and a into r cube, while 6 terms are taken as a upon r raised to the power of 5, a upon r cube, a upon r, a into r and a into r cube, and a into r raised to the power of 5.